Oh, look, perfect, a fellow nerd. Welcome. Today we're going to study the atmospheric parameters and how they vary with respect to altitude. Things such as atmospheric pressure, temperature, and most importantly for today, air density, and how these parameters impacts the flight characteristics of the jets that we all know and love. So, my dear viewer, you just managed to get your little hands on the Su-30 SM2 somehow. I don't know, either by pure hard work or by dubious means. Either way, I'd say let's take this thing for a joyride. But of course, some of you may ask yourself, what is this U-30 SM2? Well, the SM2 is a heavy multi-role fighter, a true marvel of engineering due to the fact that it is one of the few jets that possess thrust vectoring, which is the ability to move the direction of where the engine's thrust points at. However, thrust vectoring could be an entire video on its own. So let's continue. So, now that we're in the skies, let's see what is the maximum speed that the SM2 can reach. Since the SM2 is flying really fast, it is experiencing a force known as drag, which is expressed as such. Drag is an aerodynamic force that opposes an aircraft motion through the air. The other force that causes said motion is the thrust, which is the power that the engines emit. The expression to calculate drag tells us that it depends on air density, velocity of the air, the reference area, and the drag coefficient. In reality, calculating drag is a lot more complicated than just one single formula, especially when the aircraft approaches or exceeds the speed of sound. It is a process that involves a lot of simulations. But for simplicity's sake, we'll assume that this formula applies for any speed. So in this case, we know that air density, the reference area, and the drag coefficient are constant. Even in reality, they can change depending on external factors. So the only variable here would be velocity. This tells us as velocity increases, drag also increases. And in theory, there should be a speed where drag and thrust are equal, so they should cancel out. So the aircraft should not lose or gain any speed.
Interior like suicide, wrist rags, I could exercise you. This could be your phys ed. Cheat on your man, homie. Ah, I tried to sneak through the door, man. Can't make it. Can't make it. The shit's stuck. Out of my way, son! Door stuck! Door stuck! Please!
Well, that ended poorly. So what just happened? If we analyze the clip, we can see that at a certain speed, the left wing was torn apart. This happened because the aerodynamic forces were too much for the structure of the SM2 to handle. I wish I could get into depth of what really caused the wing to fail, but to do this, we need a lot of math and physics, which is well beyond my level. Hey, scat, shoo, get out of here. This video isn't about you. So, instead, we'll stick to simpler equations, and in this case, we'll study a concept known as dynamic pressure. Dynamic pressure is rather similar to static pressure. That means that per every unit area, there is a force over said area. In metric, it is measured in pascals, or Newton per square meter. Or, for my American viewers, in freedom units, it is measured in psi, or pounds per square inch. But the big difference between static pressure and dynamic pressure is the fact that the fluid is moving, hence the word dynamic, which means constant change. In this case, constant change in position. Under these circumstances, the fluid that is in motion would be the atmosphere, or in simpler terms, the air. Dynamic pressure doesn't tell us exactly why did the wing of the SM2 fail, but it is a good indicator to tell us how much force was the SM2 experiencing. Now, we know more or less what is dynamic pressure, so we can look at the mathematical expression. This equation tells us that dynamic pressure depends on two things: velocity of the fluid and density of the fluid. In this case, the density of the fluid would be the air density at sea level, and the speed would be more or less the speed of the SM2. To get the speed, we can analyze the clip. So, the game tells us that the SM2 was going at 1,521 kilometers per hour right before the disaster. Now, we can calculate the dynamic pressure by substituting these values into the equation, which gives us a number of 109,335.07 pascals. Well, that's a big number, but for you can truly grasp the insane force that the SM2 was experiencing, I will need to give you an example with the following scenario. I'm pretty sure most of you have stuck your hand out of a moving car, and all of you should have noticed that there was a force acting on your hand. Well, that force right there was drag. And another way to express drag would be with dynamic pressure. In this case, let's say you stick your hand out of a car going at 10 kilometers per hour. You might not even feel anything, but if we increase the speed to 100 kilometers per hour, you will feel the force increase. We can actually use dynamic pressure to quantify that force. In this case, we already know air density and more or less the velocity of the fluid, so we can plug these values into the equation, which gives us a number of 473.36 pascals. This means that your hand is experiencing a dynamic pressure of 473.36 pascals. Actually, to calculate drag, this number is crucial. Now the only numbers we would need would be the area of your hand and the drag coefficient of a flat hand, which would be about 1.1. So now we have a reference to understand the immense force that SM2 was experiencing. 473 is nothing compared to 100,000. So, does this mean that the top speed of the SM2 is 1,521 kilometers per hour? Not really. The top speed is set by the dynamic pressure, but if we want to increase the velocity, we can decrease the air density. This is why I said that air density is the main focus for today. We can actually deduce the variation of air density with respect of altitude using calculus. Now, we can get the formula, or in this case, the function to calculate air density with respect of altitude by using three simple equations, which are temperature with respect of altitude, the hydrostatic equation, and the ideal gas law, which are expressed as such. These calculations may look quite complicated, mainly because there are so many intimidating symbols and so few numbers. But if you actually know how to integrate functions, the math is fairly easy, and it is a really cool example of the real applications of integrals that doesn't have to do with area under a curve. It's not super necessary to do all the math yourself, but I think it helps to understand the equation by knowing where it came from. And if any of my viewers are interested of seeing where do the functions come from, well, here's all the math in all its glory. There are just a few things that I would like to clarify if anyone wants to do the math. You may see terms like P of 0 or P of h. This is not a multiplication. This refers to the function to calculate pressure at a certain altitude. For P0, this means the atmospheric pressure at sea level. And for P of h, this means the pressure at any altitude that you want. This is why this one is a variable and P of 0 is not. It is very similar to f of x, where h is equals to x and y would be the pressure. Another thing I would like to mention is that P and P are not the same. Capital P means atmospheric pressure, and P, or rho, is a Greek letter that represents density in the case of physics or engineering. Now, with these concepts out of the way, we can finally use these equations, especially the equation for air density. But one thing I would like to mention is that these equations only apply for the lowest layer of the atmosphere, which is the troposphere. Above the troposphere, the variation of temperature starts to go all wonky, which will cause our equations to fail. Although jets can operate above these altitudes, for simplicity's sake, we will use altitudes below 10 kilometers or 6.2 miles. Now, if we analyze the function for air density, we can see that air density decreases as altitude increases. This means that if we increase the altitude of the SM2, we should be able to go faster according to the equation of dynamic pressure. However, some of you may ask yourself, how much faster? Well, we can use the equation of dynamic pressure to get the theoretical velocity of the SM2 at a certain altitude by simply isolating the velocity in the equation, which is now expressed as such. In this case, we already know the dynamic pressure, and now we just need to define an altitude to get the air density at said altitude. This is exactly why we did all those previous calculations. Let's say I want to get the theoretical velocity of the SM2 when it is flying at 8,000 meters or 5 miles. Well, we can substitute these values into the equation, which gives us a theoretical velocity of 2,323.807 kilometers per hour. Okay, so in theory, the SM2 can reach a top speed of 2,323 kilometers per hour when it is flying at an altitude of 8,000 meters. But how can we test that number if we lost the previous jet? Well, my dear viewer, I just managed to get my hands on another SM2. This time, it is by dubious means. Okay, So now that we have the new SM2, we will have to take off and fly at an altitude of 8,000 meters to see if the theoretical velocity that we calculated is true. Alright, now that we're in the skies, to verify that we're currently going at 8,000 meters of altitude, we can use the HUD or the digital display to verify that our altitude is approximately equals to 8,000 meters, maybe just a few hundred meters of difference. And now that we're at the cruising altitude of 8,000 meters, let's verify that the theoretical velocity that we calculated is true. To see the current velocity of the SM2, I will use the third-person view, mainly because it gives us the most important information, which would be the current altitude and the current velocity of the SM2. This crucial information is on the top left corner of the screen, between those other numbers. However, those other numbers don't really concern us, or at least not for now. Alright, so it seems like the SM2 suffered the same fate as the previous one, but this time the SM2 was able to go way faster than the previous attempt. This was expected because we calculated a theoretical top speed of 2,323.807 kilometers per hour. If we pull up the clip, according to the game, the SM2 was going at 2,286 kilometers per hour right before the structure failed. Okay, so there's a difference between the theoretical velocity and the experimental velocity. If we plug these values into this equation, we can get an error in percentage between the theoretical value and the experimental value. Once we do all the math, we get a variation of 1.62%. Well, in engineering, we usually have a tolerance of plus minus 5% error when it comes to experiments in the lab. Sometimes it could be less, but for the most part, it is plus minus 5% error for the experiment to be considered successful. And in this case, we can conclude that the theoretical velocity that we calculated is true. Even though there is a small error, it is necessary to justify said error. Since the experiment wasn't done in real life, I used a simulator. Mainly because I don't think the Russian Air Force would be particularly fond of sacrificing two SM2s in the name of science. Even though the game tries to simulate real life physics, we must keep in mind that even the game can have mistakes when it comes to calculating the values. For example, maybe the air density that we calculated is different to the air density that the physics engine calculated. And this is just one example. There are several variables that can vary, which can change the expected value. Even though we had a low error in game, if we would have done this experiment in real life, the error would have been greater. Mainly because airflow changes a lot once we go at higher speeds. This is why I mentioned this at the beginning of the video. Near the speed of sound, air starts to compress, and these basic equations that we used do not take those changes into consideration. Well, my nerds, this class is coming to an end. So I'd like to say just a few things before we finish this class. Most likely, all of you have heard that studying math may seem kind of pointless. Hell, sometimes I even ask myself, why should I bother to study all this math? Well, actually, my dear viewer, these equations are relevant in so many other fields, like weather prediction and transportation. For example, most airliners operate at a higher altitude to take advantage of the decreased air density, which decreases the drag that the airliner must overcome. This means that they can save fuel and money because of these equations. Of course, these are only a few examples of how the atmospheric parameters affect your daily life. And on top of that, we also studied how they affect the flight characteristics of an aircraft that operates in the lower layers of the atmosphere. Alright nerds, that would be it for today. I hope you enjoyed the video. Please leave a like if you enjoyed it, or dislike it, that's also valid. If you could, please leave a comment, that would be much appreciated. Stay safe nerds, see you next class.